Hi everyone. This is the last topic in Unit 7, LeChâtelier's principle. And before we go any further, I think for about 20 years I've been calling it LeChâtelier's principle. But I just realized there's an E right there. Let's go with LeChâtelier's principle. And what he said was he gave us rules to predict how the reaction will adjust when we perturb equilibrium. For instance, let's say we establish equilibrium in terms of population of country A and country B. What if at some point country A has a baby boom and the population grows? Then what happens is, to maintain the ratio of people in country A and country B, the rate of migration has to change, with more people going from country A to country B until at such point the ratio is reestablished. Equilibrium is reestablished. But let us look at a chemical reaction to show all the different ways that Le Chatelier said the reaction will adjust when we what's called perturb equilibrium. So let me set up the problem, and at the same time we'll discuss his principle. For part A, let's say we perturb, disrupt a reaction already at equilibrium. The reaction we're going to look at throughout this whole video is going to be 2SO2. What is that? Sulfur dioxide plus O2 gives us 2SO3, sulfur trioxide. And I'm going to give us enthalpy. Delta H equals negative 198 kilojoules per mole. So we know that this reaction is exothermic. Le Chatelier said this. I did it again. Le Chatelier said this. When we change the conditions of a system at equilibrium, or when the conditions of a system change, let me restate this. When the conditions of a system at equilibrium changes, the system, in this case the reaction, adjusts or compensates or shifts. The system shifts directions, and this is forward and reverse, shifts directions to minimize that change. Or you could think of it as compensate for that change, or correct the change. But let's use minimize or compensate. The system shifts directions to minimize or compensate for that change. Okay, now before we take a look at how are we going to change the conditions, there are a couple things, a couple phrases that you may see on an exam. The exam may ask you, if I add oxygen, which side will be favored? So one way they could ask a question is, which side? Left or right? Left side of the reaction or right side will be favored. Now, we got to remember that it's only going to be favored temporarily until equilibrium is established. So that's unspoken. So they mean which side, left or right, will be favored until equilibrium is reestablished. So I'll put that in quotes. But that is typically, they don't have to state that until equilibrium is reestablished. So that's one way they could ask the question. Another way, let me make this a question mark. Another way is which side does equilibrium shift to? Okay. Now, I should have mentioned in the beginning, at equilibrium, and we all know this, but I think it's good to visualize what's really happening at equilibrium. The rate of the forward process is the same as the rate of the reverse. Remember what that's called? That's specifically called dynamic equilibrium. So at equilibrium, these are identical. And then when you perturb the reaction by either heating it or adding an inert gas maybe, or removing some of the product or adding more of the reactant, when you perturb a system where this is true, then one of these is going to be favored until you get to a point where the concentrations or the pressures get back to your Kc or Kp, right? So what else do I want to put here? Oh, maybe I'll mention also that up here, Kc equals 3.5 times 10 to the minus 7. So we know that we have, it's less than 1, so we have many more many more reactants than products. All right? Okay. B, C, D, E are all ways we're going to change this reaction, perturb the reaction. So let's do B first. B is if we add, let's say we add SO2. Okay, let's do that first. So if we add SO2, okay, look at our reaction, then that means that when we calculate QC, QC is too big. So if we add SO2, is that right? No, QC is too small. So if we add SO2, that is the reactant. What happens to the QC? Oh, by the way, maybe we should also put at equilibrium QC equals Kc. They are identical. Remember, QC is a way to tell us, well, we've said this before in the past, which way the equilibrium will shift, or which direction the reaction will go in if QC is too big or QC is too small. Well, if we add SO2, the reactant, we are making QC, see, it's products over reactants, so we're making QC too small. QC will be less than Kc, and what that means is that we need more products. So it's going to shift to the right. Ultimately, a lot of the problems with LeChâtelier's principle, the problem's going to ask you, does it shift to the right or left temporarily? That's your answer. Shifts right. But you could also visualize this. If we add SO2, like visualize a little arrow going up like this. What does the reaction have to do to get rid of that excess SO2? It has to go to the right. So honestly, I typically don't think of QC when I'm doing these problems. I literally do this. 2SO2 plus O2 goes to 2SO3, and when I add, I put a little up arrow, and I ask myself, which direction do I need to shift to get this back down to equilibrium concentrations? Now, it won't get back to its original concentration because as you're consuming this, you're adding more of the product. So it will go down when the reaction shifts to the right, right? You'll start consuming the excess, but you'll reach equilibrium actually before you get to the original concentration. That's a subtle point right there, because you're also adding this as you're consuming your excess or your added SO2. So I'm going to use this technique, the arrow technique, rather than the QC technique, because the other one is if I remove O2. Okay. How will the reaction shift? By the way, when I say shift right, what does that mean? The forward rate is now larger than the reverse rate, and it's going to stay that way until QC equals KC, till we get back to equilibrium. So if I remove O2, I visualize a down arrow here. So I don't have enough O2, so I need to shift to the left. It's as simple as that. Okay? But you could literally prove it by calculating, if they gave you numbers, you could calculate QC and show that, oh, QC is too big, and if QC is too big, you got to consume some of the product, and you will shift to the left. The last one, so B is just changing, right? Changing the amounts of products or reactants. Very often, especially in organic chemistry, you can remove product as it's made. Why would you want to do that? So let's pretend. If I remove product as it's made, I got to replenish that product. So it's kind of a neat way to push the reaction forward, because you're continually removing product. Equilibrium, for it to be reestablished, you have to keep making more product to maintain that KC. So yeah, it's kind of a tricky way to get a lot of product, even if your KC is very low, because you just keep removing product and the reaction will adjust and will keep adding more product and more product. So this will shift to the right. Okay. And again, what I'm visualizing is a down arrow here. So forget about this first green arrow. If I remove product, what do I need to do to replenish it? I got to shift the reaction to the right until KC, until equilibrium is satisfied. So let me just do this. This green arrow is for the first part, the first perturbation. Okay, that is adding material, either adding reactants or products. Now, what about temperature? Okay, so this is part C. What if I cool the reaction? No, what if I raise the temperature? We'll do that first. Normally, right, raising the temperature pushes the reaction forward, but we got to be very careful. It really depends on whether your reaction is endothermic or exothermic. So how would I deal with this if I raise the temperature? Well, this is what I would do. I would literally make heat a product or reactant. So just remember, all of this is gas, so I'm not going to put the phases for this this time, but I'm going to remind ourselves that delta H is negative 198 kilojoules per mole, and that is exothermic. So literally, I'm going to put the word heat. But where do I put the word heat? Do I put it as a so-called product? Or do I put it as a so-called, oh, sorry. Do I put it as a so-called reactant on the left? Or do I put it as a so-called product on the right? It's giving off heat. It's negative. I'm going to put heat right here. H-E-A-T. So I'm thinking about it as a product. Now, if I raise the temperature, what do? The trick is, well, I'm going to put a little arrow here. I'm going to raise the temperature. I'm adding heat artificially, not from the reaction, but I'm adding heat by, I don't know, putting it over a Bunsen burner. So what happens here? To compensate for that extra heat that I'm giving, it has to shift to the left. It has to use that heat. It has to consume that heat. So this is an interesting case where when you raise the temperature, you actually produce more reactant initially, and then you'll get back to the equilibrium constant. But yeah, you are shifting to the left in this case. So if I cool or ice the reaction, that means that the heat is going down, and I need to replenish that heat. So now it shifts right. You could try to memorize it if you want. You could say, well, for exothermic reactions, if I raise the temperature, it shifts left. If I cool the reaction, it shifts right. Or, if I was trying to do that, I'd be very afraid that I would get it backwards. So, or you could think of it as, well, let's make heat either a reactant or a product. Now, if it was endothermic, you have to add heat to the reaction. You would put the heat on the reactant side. And then, just like we did for these two examples, think about that as a substance. And either you're adding to that substance or you're removing that substance. Just like we did here, add and remove. That's temperature. You will need to know to do a problem like this whether the reaction is endothermic or exothermic. Part D, increase volume. This one's interesting. Increase volume. So for instance, if we have a piston and we have these gases in that chamber right there. So we have SO2 in blue, we have O2 in green, and we have SO3 in pink. Or what if we increase the volume? If we move the piston up, piston goes up. This is a little bit tricky. If the number of moles of gas is equal on both sides, then nothing happens. Volume, changes in volume do not shift the equilibrium. Changes in volume do not shift equilibrium. This is our first instance where there was no shifting involved. Okay. But we don't have that in this case. We have SO2, and I'll put here now gas. O2 gas goes to 2SO3 gas. Okay. This is tricky because when you change the volume, you are changing the concentration, right? You are changing the moles per liter of each of the components. It's just that when the moles of gas are identical, the number of moles of gas are identical on both sides, not only are you changing the concentration, proportionally to each other, you're also changing the numerator and denominator in the Kc expression. SO3 squared over SO2 squared O2. So the denominator and the numerator are changing proportionally to each other if the number of moles of gas are equal on both sides. If they are not equal, which they're not equal here, then actually the denominator and numerator change. They're not proportional when you change the volume. So here, this has 3 moles of gas. Over here, we'll say we have 2 moles. Okay, so equilibrium will shift with volume. And here are the rules. If you increase the volume, you go to shift towards the side that has less gas. That has less. Oh, wait. I messed up. That has more gas. If you increase the volume, shift towards the side that has more moles of gas. So in this case, we are going to shift to the left. And vice versa. If you decrease the volume, shift to the side that has less moles of gas. So in this case, if we decrease volume, in this case, we're going to shift to the right. Okay. So remember those 3 things. Remember this bullet point. If the moles of gas is equal on both sides, the changes in volume do not shift the equilibrium. Okay. But if you have an unequal number of moles of gas on each side, then what really happens when you increase the volume is not only does the concentration change, but the ratio changes. Okay. So in this case, when you increase the volume, it does shift, and you will shift towards the side that has more moles of gas if you increase the volume. And if you decrease the volume, shift to the side that has less moles of gas. So you have to do this analysis, how many moles of gas on each side. Let me just double check this last one. If you decrease the volume, yeah, you want to shift to the side that has less moles of gas. Shift to the right. Last one, and it's an easy one. Part E, if we add an inert gas. Part E, if we add an inert gas like helium. Well, inert means that it doesn't react. It doesn't react with reactants or products. Therefore, reactants and products concentration doesn't change. And if the concentrations don't change, and we're not changing the temperature, the equilibrium doesn't get perturbed. So whenever you add an inert gas, there's no shifting, period. Because again, when you look at the Kc, and you have your concentration of SO3, 2, over concentration of SO2 squared times the concentration of O2. Adding an inert gas does not change the concentrations. So there's no need to shift the reaction. Okay. I will leave it at that. You got to also assume that no matter what you're given, either Kc or Kp, this is true. It does not shift. There's no shifting. So don't get sidetracked if they give you a Kp. It's still equilibrium, and equilibrium does not shift, period, when you add an inert gas.